Hello. Wow, look at all of you here. That is amazing. Hello. Oh, and you even knew what to say. Oh, see, I didn't even know if you knew. I couldn't even remember if you, oh, I'm so touched. Okay. So good morning, Ruby. Hello, Joseph. Good morning, Karen. Good morning, Athia. Good morning, Alyssa. Good morning, Manoj. Good morning, Zimin. Or did I say? Yes. Oh, wow. And who else did I? And good morning, Antonique. Good morning. Did I say Manoj? I said Manoj. I said Zeman. I said Alyssa. I said Athia. I said Karen. I said Joseph. I said Ruby. Oh, I even see video. Amazing. Amazing. Hello, Carly. That is amazing. No, I really appreciate on all levels. Good morning, Carly. Oh, good morning, Carly. Right. Okay. No, this means a lot. I am terribly sorry about this. I'm very appreciative that you guys are here on Zoom. It's a totally stupid way to end, or it's like a disappointing, for me, it's a disappointing way to end. But my disappointment is changed by seeing your bright and shiny avatars and faces. So yeah, I'm stuck here. Couldn't get out. More people coming. Okay. This is I guess I made it. Well, you obviously you guys got the thing, and you're getting points for the thing that you got that said we're on Zoom today. I'm not sick or anything like that. I just could not get out of the airport, which has happened once before and is totally annoying. But anyway, so here you are. That's awesome. Here I am. Okay, and now and it's good that you're here. And it is still true. Okay, a couple of items of logistics as far as points and things like that. For sure, all of you that got this message about today and returned it, you're definitely getting those points. It is still not too late, and might be helpful to hand in anything that you want that you think you can get any points for at all. Even, for example, like those views, like not to mention anybody by names, but for example, Carly's showing video, she can totally hand, it is not at all too late for her to find that game turn thing that's somewhere in the Google Classroom that says video. She can turn that thing in and get some points for that. Any one of you who's showing an avatar right now can hand in that thing that says avatar and get some points for that. One of the reasons I'm glad you're all here, and there's more people coming. One of the reasons that I'm glad you, well, I'll wait for a second. Okay. I'll let her, hold on a second. one of the reasons that I am glad that you were able to make it today, even on Zoom, and one of the, sorry, right, I'm sorry. Oh, that's right. And now you reminded me, Joseph said, what is avatar? Maybe I'm using the wrong word. I might be using the wrong word because I even know what Joseph's is. So by avatar, what I mean, but I'm using the wrong word, I think. I mean is like right now, for example, and this is not a big deal, but like right now, for example, Joseph, your thing is like a black square that just says your name, Joseph McDermott. So I totally know you're here and I totally appreciate that. And I know you're listening because you just asked that question. So one thing I'm just saying is, even though it's the very last class, there's game turns that you can submit, like just for the fact that you even just asked that question, that you participated, and you'll get points for that. But also, if you, good morning, okay, thank you. Good morning, Jessica, and good morning, Nick. Awesome. Hello, both of you. Thank you for making it. I'm just answering a question here, and then I'll go back to the thing. Joseph, by avatar, I just mean like for example, I don't know if you could see on your screen. I mean, I think you can. Like Althea hers is not a black box. Like you could see a picture of her, or Manoj, you could see a picture of him. But Jessica's, I guess, is more what I mean by an avatar. By avatar, I mean, even though I'm using the wrong word, I mean if you put any image up at all, anything that distinguishes you, that just is just like easier on my eye than a black box, or that just makes, it's not really that important for this class because we've been live all semester, but for this, like Antonique just did, right? Like that, or like Ruby has, and now Jessica's totally live and in video, even more exciting. I mean, I don't want to spend the whole class talking about this, but those classes that meet all the time on Zoom, I give them extra points for just like being alive or different or distinguishable in any way. So, and I know you, Joseph, for example, I know you on your work, on your written work, I know you have an avatar that is, again, I'm sure I'm using the wrong word, but you have like a little, instead of just saying JD or something, it has a little picture of either Luxio or Luxray, or the evolved version. One of the evolutionary lines of the Luxray Pokemon is yours, I'm pretty sure, right? I mean, it's that blue and black, right? And anyway, the point is, this is all silliness. Yes, okay, cool. So that's what I mean by avatar, even if I'm using the wrong word. And I'm just thanking the people that are showing anything but a black box, because it's like less depressing. But here's what I'm really here to say to everybody, especially like Jessica who's just joined, or Nick. Like the reason I'm a profile picture. Thank you, Althea. Yes, a profile, right? Which Althea totally has right now. And I'm just indicating, and when I say avatar, I guess I'm just trying to say that it doesn't even, it's super nice if like I actually get to see what Althea looks like or whatever, or learned what she looked like last semester. But even if it's just a picture of a Pokemon or something that just shows me like what you identify with. Anyway, I'm going to stop talking about that. The reason I'm excited you're all here, first of all, is because, again, I want to say for one more time, even though I've made the speech before, like I am going to miss you people. It's been a very like intensely emotionally challenging couple of years for everybody. Therefore, I feel even more emotional about it than even usual. So I really am going to remember you people, and I will want to see you again or write recommendation letters for you, blah, 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 blah. But the other reason that I really wanted to not cancel this last class or to not miss it is, like, I want to make sure that we leave all of us with the maximum learning possible. Like I want to make sure that even on this last day, even if there have been mistakes along the way that I've made or imperfections that you've experienced, I want to make sure we all have one more chance to learn the end of the physics story, because there is, or at least the end of this physics story, this semester, or these 2 semesters for some of you, have actually been meant as a kind of physics narrative, whether it seems that way or not. And there is a last chapter to that narrative that makes all of it make a lot more sense once you hear the last chapter. Like I believe that you'll see that there was kind of a point to all this math that you were grinding and all this stress that you're experiencing. I believe like there's a point to this physics story that is kind of the point that keeps me excited and keeps me wanting to do physics semester after semester after semester with people for real. But also, so I want to share that with you. Like, I kind of feel like you put in all this work and all this effort and getting up at 8, for an 8 o'clock in the morning class week after week, you should at least see like the end of the science opera, but or at least give it, I mean, you might not like it still, but at least it will have given you its fairest shot. But then similarly, in reverse, after all the work that you've put in and the anxiety that you've had to experience with some of you still not even knowing what your midterm score is, and I know that, even with, and I feel terrible about that. So even with all of that, what I want to make absolutely sure for everybody on this last day is that everybody knows that everybody still has a solid chance to walk away from this class with a solid grade, even if you haven't felt that way up until this moment. In other words, what we're really going to do today is some of you still have not gotten your midterm scores back. I just said it. I'm going to say it again. And I'm not saying you're going to have them in an hour. Some of you still won't have that score. But what I want you to have instead, and that's terrible, and I apologize, and there's nothing I can do about that in this next hour. What I can say to you is, again, I want to make it clear, since you're all here listening, is that if it hasn't been made clear before, you're not being graded on your middle in this class. You're being graded on your best. That is to say, like, some of you do a lot of class participation and then turn in a lot of game turn points and talk a lot and show me your notes a lot and make your contribution clear that way. Some of you did rock the midterm, got it back or didn't get it back, or will have found out that you rocked the midterm. Some of you rocked the midterm once you did the 14-point thing and you rocked it that way. Others of you will rock the final. What I want to make it clear again is whatever you did the best at is going to help your grade the most heavily. There will be the most weight put on what you did the best at. In other words, if you give me something to work with, each one of you who's given me some way to mathematically and legitimately and fairly, like as long as I use the same math for everybody, which I will, as long as I use the same grading system for everybody, which I will, that system is designed to favor the best of each of you. So for each of you, as long as by the end of next week, you've given me something that is workable, that will evolve itself into the highest grade possible, hopefully for most of you, like an A or an A minus, or horribly a B plus or B or something like that. But you won't be graded on your middle. You'll be graded on your best. Your worst will not count heavily against you. It'll just be there at the bottom of the pile. So I'm saying, so everybody has to take this final that we're going to explain for the rest of this period. Everybody has to take it. But if it turns out that you rock the midterm, and then the final won't hurt you heavily, is what I'm saying. Don't be scared of it. Look at the final as a way to help if you need it, and it won't hurt you that much if it turns out you didn't need it. Conversely, if it turns out and you find at the last minute, or you just know in your heart sinkingly that you just never did do well in the midterm and you don't even need to see the number to know that that's true, then rock the final and it will help you. And we are going to spend this period talking about the final. You'll see what I mean in a minute, but that's why it's kind of really good that you're here. I think anybody who's here is going to do fine on this final, more than fine. I think, and by the way, I'm saying if you're here, like if you're here hearing my words right now, even, I know it's a long class and it's an early morning class. So even if you like walk away and come back and get a cup of coffee, let me really encourage you to watch the tape. I mean, the video or the videos of the other two sections. Like this is one time where over the next week, you really might want to go to the YouTube and check out, because what we're going to do once I get rolling in a second, once I've answered any logistical questions or things like that, I'm going to start banging through the very last material of the course. It's not going to be very mathematical. It's not going to be very like a bunch of stuff that you have to memorize. There aren't even going to be a lot of notes. It's going to be very conceptual, for like very Englishy. For some of you, that will be a huge advantage and a huge relief, change of pace. For some of you, it might seem very abstract and heady and like, whoa, what's he even talking about? And because it's a long class, you're totally welcome to stop and ask me questions, of course. Oh, yeah. So sorry, I see the chat. Like Karen, the answer is totally yes. And that's exactly what we're going to do. I'm going to tell you how it's going to go. No, that's exactly what we're doing. Exactly. Like you're here, we're here to practice in effect for the final exam. And I'm going to explain how it's going to go, but yes. So if you see Karen's question in the chat, yes. And I'm glad you put that in the chat. Again, the one advantage we have in this class is it's a little bit longer. So once I get rolling, you definitely can't, like, I'm going to start talking kind of, yeah. So, okay. So Ruby's question, the answer is yes. I'm going to spell this out very precisely, but the answer is yes to Ruby's question about Google Forms and the final exam. The good news is yes, the final exam is a Google form that is literally like, I don't even remember how many questions, it's like 20 questions or something like that. And like 19 of them are true, false. We're going to talk in detail about that in a second. And by the way, that's good. Like Karen's question and Ruby's question. Oh, good. Okay, good. I'm glad if you're happy about that. And I think that their questions indicate, no, good. Oh, I can see double hat. Oh, and Carly, oh, this is cool. I can see like different forms of happiness. Okay. No. And that's totally what we're going to turn our attention to explicitly in a moment. And that's why this is worth your time. I hope, I feel it'll be worth your time that you're here. What am I going to say? And I'm going to take it from Ruby's question, and Karen's and Anthony's. I'm going to take it that you're able to access the form. That's good news in itself. That took us like 20 minutes in one of the other sections. So if you can access it, we've already saved a big part of the problem. So here's the deal. Yes, believe it or not. So let me just I'm going to say the logistical details, then we're going to start doing the physics. Let me just change it. And again, obviously this is all being recorded. So once I start doing the physics, I didn't mean to do that. Once I start doing the physics, I will be talking a little intensely. Like now, I will be talking a little fast because I get excited and all that kind of stuff. If I talk fast or talk intensely, it does not. Yeah, totally, Joseph. The answer is yes. And see what's happening right now. These questions are great questions. I'm going to answer them all. I will stop and answer questions like this. You can keep asking them. I keep forgetting that I should read them out loud because some of you. So Joseph's question is the final exam like the practice exam? I mean, is it true or false? Believe it or not, yes. Like I promised you guys, and I mean it, this exam, the material, you'll see if you look at it right now, the material is not easy. The material is kind of weird and conceptual. Like some of the questions at the beginning, hopefully you know the answers because they're from the beginning of the semester. But as you start looking through, the questions might look weird and conceptual and or I'm not abstractly sciencey because this is a physics class. I think some of those questions you couldn't possibly, if you just literally guessed your way through the whole thing randomly, or if my mother did, with all respect to my mother, I love my mother like a mother, but if she just like randomly guessed all the questions, she'd get a 50 at best, which is like not the score anybody'd be looking for. You have to know the physics in order to get it right. And you will know the physics by the end of today. But yes, hopefully it's not too stressful to take and hopefully it doesn't take too long to grade. Yes, your final exam. So let me be clear about these logistics. Your final exam, your actual final exam will be posted tomorrow night, Wednesday night, because that's the beginning of finals period. It'll be posted tomorrow night, like no later than 8 p.m. or something like that. It'll be due back next Monday night at 11:59 p.m., like pretty much the second, almost the last night of finals. So you'll have from Wednesday to next Monday. You could do whatever you want in between. You can and should talk to other people, believe it or not. I'm not going to post the answers, but you can talk to other people, et cetera, et cetera. All of the questions are true, false until the very last one where it asks you to take like a half a page or so to put down whatever equations, pictures, words you can to summarize the whole, what you've learned. Okay. And that's where you'll free express yourself for like a half a page. And even there, the point of that is that I won't take away points for badness, but that will be your opportunity to get as many more points as you possibly can to really show me that you know what's going on, or show me what you've learned, or show me your perspective on the material. But other than that last question where it asks you to freely put together the material in like a half a page, all the rest are true, false. And I'm telling you all right now, not only are they all true, false, not only will it look that format, like Joseph's asking, like Ruby's asking, like other people are asking, not only will it look like that, I'm telling you right now, that document that you have in front of you that apparently you're accessing, and I guess people have already, the document that's in Google Classroom that says practice final exam, which I do hope you do access right now. And I do hope you open up, and I hope you hold in front of you for the rest of this period while I talk. That thing, oh, it is your final exam. The only thing that's going to change to Wednesday night is I am going to scramble the order of the questions. That I am going to do. The order that they're in right now is pretty much the order of the material. It's the order of the course. It's the order of the story. It goes from kind of simplest to most complex or abstract. And it goes pretty much in the order that I'm going to talk today. I'm going to start somewhere in the middle because those questions start from the beginning of the semester. I'm going to start somewhere in the middle, you'll see. And once you see the first question that I hit when I'm talking today, pretty much you'll be able to find the questions while I'm talking. They'll pretty much go in the, so I'm asking you to follow along while I talk today. Just try to listen to me by looking at the questions. Like I'm literally, okay. And when you get the actual final exam, it's going to be, wait, right. Wait. Hold on. Wait. Okay. Let me answer Karen's very good question in chat in 1 second. I think I understand Karen's question. Let me just say one thing and then I'll answer it. What I want to make clear is I'll answer it. This practice is for practice. It's for following along right now and for you to do it. It's not for handing in. You're not actually getting points for this practice. It's literally for your practice. I mean, yeah, it's literally just for your practice. As far as extra points to help you in your grade and all that, I'll say this. You might notice that the game turn for today, like, you know how every day we have a regular game turn that you hand in, and it's usually worth 5 points. Today's, if you notice, is worth 15 points. Now, I don't mean 15 exam points. I do mean 15 homework points, which is not exactly the same thing, although it almost turns out almost to be the same thing in my grading system. So if you do follow along today and you follow intensely and you, and even if you ask one question for clarification or something like that, or as long as you've been here, if you fill out tonight's game turn, that's 15 points instead of 5 as an encouragement to really hang in today with me. So that you'll get points for. This practice exam here, you don't turn it in ever. It's not for, okay, thank you, Karen. So what I am saying, private chat person, I'm saying that once I start talking today, I am talking right now, but once I start really talking about physics, my lecture today is basically going to be the answers to that document that you have in front of you. Sometimes I will literally stop and say, oh, and so this is one of the questions. Look right now, what I'm saying, look right now. And I'm telling you the answer to that is false. Like sometimes I will literally be that explicit. Other times I won't. Other times I'll just say physics things. But if you're watching, instead of like scrambling and taking a lot of notes, if you're okay, great. Okay, thank you. So yes, so I'm telling you all today, my lecture today will essentially be the answers to those questions. That you have them in front of you to kind of like help you pay attention to me and help me know that you're paying attention. And then what I'm saying is Wednesday night, when the final exam is actually posted, it will be those questions. It just with 2 catches. The order will be scrambled. So you can't just go like TF, whatever. And in some of the cases, I will change some subtle words like the word not. Like I might take one of the questions and literally, even if it's phrased as true right now, I might rephrase it so it becomes false. So I'll make little changes like that so you actually have to pay attention and actually understand what I'm saying. I'll be a jerk like that. But the content, the material, the basic questions, they won't change. That is the final exam. And again, it'll be posted Wednesday. And again, you can and should talk with one another. You can and say like, did he say this or what did he, if he said that, does it mean in question 20, it's this, blah, blah, blah. You can. I'm never going to post literally. I'm not going to post a thing on the web that's like TFFFFT are the answers. I'm not going to do that. But yes, once I get going today, physics wise, everything I say today will be the answers to those questions. And those questions won't be surprises. You should have them in front of you while I'm talking to see what's going on. And of course you could stop me and ask questions while I'm going. You can be like, wait, so the answer to question 18 is false then? And I'll answer, because the more you're paying attention, the happier we are. And the more that helps your colleagues, the happier we all are. Okay, so thank you for a direct chat person. Cool. So we're going to start in a couple minutes. But again, as you can see, I get a little intense about this. I just want to make it as this weird method of like pivoting and making our final exam different like this. I mean, obviously, partly it's to try to fulfill every promise I'm trying to make to you, which are all promises being made as an imperfect human being who makes mistakes and screws things up, like didn't finish grading your midterms. Totally on me, totally bad. But I still want an opportunity to end nicely with you, both in the physics sense and the grade sense. Like, I have a physics story I want to have given you by the end of this semester. I want to have put it from my mind into your mind. That's my goal. And I want you by the end of the semester to have a legitimate opportunity to legitimately earn an A for having absorbed that story. Today is our chance to do that together. I know it sounds cheesy, but that is really what I mean. Okay, so it's not a trick. It's just another thing of like, and also we both know we don't need another huge level of crazy complex stress this week or stressful thing to grade. So yes, so once we get rolling, I'm gonna like preach this physics at you. You stop me whenever you don't understand something I'm saying, or wherever you think it might relate to something in the document. Feel free to stop me. The only thing I will ask, because sometimes I get on tangents that I think are interesting, but might not be helpful to you. And sometimes not so much in this class, but sometimes in some classes, people have a tendency to ask questions that are really cool and interesting, but are sort of off to the side. That we don't want so much today, right? Today we want any question that in any way relates either to the material that I'm saying or relates to your concerns about how the grading works. You can stop and ask me. My goal is to get this physics into your head. Your goal is to get an A. We can do both. So any question at all, where there's any concern about either one, like the exact physics I'm saying, or how will this make you do well, you can stop and ask in the chat or whatever. But anything else, let's keep to the side. All right, so let me just see. So we're going to start in a second. So first of all, let me make sure. Hold on, I'm going to change the view of this again. Let me just make sure. Can I get from all of you? So I'm looking at Karen's. Wow, that's really cool. That I guess that not of Avatar, but whatever it is that Karen's got going on. That's really cool. I don't know what these images. Okay, anyway, they're all very cool. And hello, Jessica, and hello, and hello, Carly. Can I get Carly? Can I get an electronic thumbs up from anybody who has the document in front of them? Like if you have this Google form that I'm talking about, the practice. Oh, wait, really good point, Athea. Oh, wait, okay, wait. Oh, and thank you for the thumbs up. Hold on, two things going on at once. Wait, keep the thumbs up for a second. I want to answer Athea's question, but I just got, so wait, put the thumbs up again if you've got the document in front of you, like if you were able to open it and access it. So thank you, Jessica. Thank you, Manos. Thank you, Athea. Thank you, Joseph, Aaliyah, Alyssa, Antonique, Karen. Ruby got it. All right, so that's it. Carly got it. And Zimin, are you with, wait, did you get? Yes, okay. And and Nick has it. All right, good. Okay. But one thing, Athea just asked a really, yes. No, the Jessica Athea observation, totally fair. And let me also say, very legitimate. That's the kind of thing, even once I get rolling and I sound really intense, if you notice things like that, yes, I do want to hear them. Okay, so thank you for pointing that out. I didn't realize that, but I know why that's happening. It's not a bug on your end. It is a mistake on my end. I know why that happened. That will be changed. That's a mistake. That is a mistake. And it's not your mistake, it's mine. That will be changed for the final exam. I know why that happens. Wait, you're saying it happens a lot, but not all the time, right? Like some of the questions say true or false, and then some of them just say option one. Is that what you're, okay, I might even be able to change it right now. But here's the deal. That's also why this is a practice or a rough, because there's something else true about your rough, your 3 questions like that. 3 of them says option 1. Okay, thank you. Okay, this also proves you're all totally paying attention. Thank you. That's a mistake on my part. I know why that's just a mistake. It will be fixed. I'll tell you 2 things. Number 1, on the actual final, I can guarantee you that every single question will be a true false question. I might even fix it while we're talking. I mean, if it says that, that's a mistake. All of them are meant to be true or false, except for the very last one, which is open-ended. The very last one is meant to be open-ended. I would like you to give me something like a half a page to a page for the last one, or whatever room it gives you. If you want to submit an extra document, great. Again, even that very last one is not meant for me to take off points for you, but it's meant for me to give you more points. You can consider it like it's extra credit in that sense, like the 14-point thing was for the other exam. Like the more you do there, the more extra points you can get. If you don't do very much, then you'll just get like 2 or 3 points. But that's the other thing that's not true about this practice exam, is that the points don't work correct. Whatever it says about the points is not right. Like, because I don't remember how many, maybe you could tell me, I don't even remember how many questions there ended up being there. I didn't have time to count. So if there's 25 questions, then if there's 24 questions, then each one of them would be worth like 4 points. And then, sorry, if there's 25 questions, each one of them would be worth 4 points. If there's 20 questions, each one of them would be worth 5 points, like that. But it may not say that right now. So that'll be, there's actually 25. Okay, so there'll be 4 points. Also, maybe it is correct, actually. Okay, but yeah, any errors like that, like option 1, I will fix. I might even fix right now. Let me see if I can actually. Well, yeah, it may be a waste of time to try to fix it right now. But thank you for. But anything else you notice like that, definitely let me know. Especially if you notice something weird in some of the words of the questions, definitely let me know. Like once I start talking, you could stop me and say like, is this related to question 13 or whatever? And I'll say yes or no. Again, you can consider this class, partly anything we do today is like the reward for being here. If you feel like I'm giving away a lot of stuff today, I am. That's what I'm trying to do. I'm trying to get you to know this physics. And always just remember too, you're allowed to share this information with anybody who's not here, but that's your choice. Like you don't have an obligation to do that. But okay, wait. So all right. So everybody said they've got the document in front of them. I'll just make sure I have it in front of me too, just in case. Hold on, but I have to have other things as well. One second. Okay. Just making sure I've got it in front. Okay. Actually, let me also ask you one thing. If I do this, if I make a change right now, it doesn't show up. If I make a change right now, it does not show up on your side, right? I can't imagine. Like just do me one favor, just to make sure. If you go all the way up to the top, does it say the final exam? Right under where it says JJ Physics, all the way at the top in the form description. Does it say the final exam or does it say pre-final exam? Oh, thank you. All right, wait. All right, you know what? Okay, since we do have a little time, I'm going to take a second to thank you. Thank you all, but thank you, Karen, for putting in, and it says, oh, it does? Wait, that means, oh, okay, wait a minute. If that's the case, oh, okay, then I'm going to make these corrections. That means I never knew this. That means if I make corrections right now in real time, it means as long as you hit refresh, it updates yours in real time. I mean, I guess I should have assumed that, but then that means I'm going to fix the things that you're saying right now. And that means as we go through, if you find errors or ambiguities, we'll fix them right now in real time. So there won't be, blah, blah, blah. So, okay. So give me a second. I'm going to fix the things that you just told me about option 1. That's really helpful. So we're doing this together. Oh yeah, I see what you mean. Okay. Wow, that's really good paying attention on your part too, that you found that, Althea and everybody else, that you found where it didn't say true, false so fast. Okay, I think I'm, okay. And someone just joined us. Okay. Um, okay. And someone just joined us, sorry. Okay. So if you hit refresh, can you tell me now if there's any other errors or weird things? Obviously, you may not know the answers to some of these questions. That's what we're gonna, but if you hit, and also I should add, all of them have red stars next. All the questions should have a red star in the right, meaning they're all required. Like they should all be required. I don't even know if that makes a difference, but just to be clear. So, it's still, it does? Oh, wait. Oh, wait. Oh, but you see the change. Thank you, Althea. Thank you, Alyssa. Jessica, maybe hit, oh, and Karen says yes. Maybe hit refresh, Jessica. It has a change. Thank you, Antonique. No more option one. And thank you guys. See, you guys pay such close attention. God, I'm gonna miss you. After you, but says true, false. Okay, so Ruby, thank you, Ruby. Thank you, Carly. But now I'm worried about Jessica. She goes through all this trouble to show her video to sit in the front row, and then this happens. Is there no justice in this world? So I'm just gonna pause for a second, just to. Okay, maybe. Okay, well, thank you. All right, maybe so. The blank question is in the middle. The blank paper question is in the middle. Is in the middle. Wait, that's interesting. The blank paper question is in the middle. Wait, oh, does that mean that the order? Hold on, I think so yours may already not be in order. Hang on, I see why. Hold on. Wait a minute. That's really interesting. Is that true for other? If the blank paper, if the like free response question is in the middle, that is worth me knowing, because that means it's already scrambling the order, which means it's going to be a little harder for you today than I want it to be. Hold on, let me just fix. Oh, okay. Hang on. Good call, Ali. Well, all of you, good call. But I see. Okay. Okay. Um, Hold on. Okay. I'm hitting hit refresh. Well, let's make sure these questions are in order for right now, so it'll be easier for you to follow me along. And it's funny, I don't think this was true in the other two classes, and I don't think they noticed it. So if you have friends in the other two classes, you might want to tell them. But tell me now. Hold on. Where? Okay, I'm looking to chat. Wait. Now it's at the bottom. Okay. Huh? Yeah. If you. Okay. Okay, great, great. God, how many years have I been doing this that I'm just learning now? That I'm so glad these things update in real time like that. I mean, of course they should, but nothing ever works the way it should. I mean, airplanes should also take off when they're anyway. It says each question. I thought I just changed that. Okay, okay. So wait. Thank you. All right. And again, this is good because we do have this time. This is why we're here today. So first of all, thank you for catching. So I put the questions back in the order. It sounds like if you see that open response question at the bottom, that means that the questions are in the proper order for today, meaning they'll be easier for you to find where they're in kind of the order that I'll talk. And I also want to add, the reason I care about the order is it's not just that they're in the order that I'll talk. It's that, again, I keep sort of saying, like, this, science is in an order, right? Like, they're in an order that makes sense right now. If you're trying to make sense out of what I'll say today, it will make more sense to look at the questions in that order. So I'm glad that you all just told me that and that we just fixed that. Now I want to warn you again that once I post it as the actual final exam, I will scramble the order of the questions then, just so that you actually have to read them, and know the material by then. I do want you to know physics. Again, I'm hoping everybody gets an A, but that's because I'm hoping everybody earns an A, if you know what I'm saying. We're making this as compassionate and flexible as possible, but still in the end, when you get a really good grade, I want you to know that you deserved it, that it wasn't just given to you, blah, blah, blah. You get my point. So the questions will be scrambled in order Wednesday night, out of order. And again, please note, like, some places I will change the word literally from, like, I'll add the word not or something, just so that you actually have to read them and you actually have to know the concepts, and you can't just memorize a sequence of T's and F's. Okay, but other than that, they're not going to change. That's why you're going to pay attention today. So I'm glad you just fixed all that. I hope that's still clear. But now I see what Antonika is saying, that the points are now worth 50. The questions are worth 50 points. I'm going to try one more time to change that. If I can't, I'm not going to worry about that right now. I'll just worry about that for Wednesday night, but I will try one more time to fix that. Whoa, hello. And as you know, is Yiddish for damn, yo. Hold on a second. The best thing in Brooklyn is that sign outside the Brooklyn Museum that says "Oi" if you're driving in one direction. It says "Yo" if you're driving in the other directions. That's like the most. If you live in Brooklyn, you know what I'm talking about. It's on Eastern Parkway. It has the most brilliant thing. I don't know if it's still there actually, but all right, hold on. But I think that's why I'll always miss New York. But hold on. Okay, I'm just trying to fix this point value thing. It says every question's worth. Where does it say every question's worth? Where does it say that the question's worth? You're saying, I believe you that you're saying every question is worth 50 points, but where does it say that? It says next to every question, beside the asterisk. Huh. Because that's not on my side. I totally believe you. Okay, I'm going to take one more second to try to fix that so that it's not messed up for you. And then we're going to get rolling. It does after. All right, I totally believe you. I just can't. All right, hold on a second. Oh. Yes, I do see that. Okay. Oh, that's so annoying. All right. Hold on, let me see if I can fix that fast. Oh, all right. Give me one. I will fix that right now because that's why we're here. All right, I'm going to fix that right now, make them 4 points. But as long as I'm going to do that, while I'm doing that, if you all could scan through and find any other either errors or unclear things or anything, not about the physics itself, obviously, that's what I'm going to talk about, but anything else that's in any way unclear or disturbing, find it now. Because the way to do the points is really stupid. Oh, there's got to be a better way to do. Okay, let me know. Oh, um, okay. You see now. Oh, thank you, Joseph. That's helpful. Wait, but now thank you for saying that. And I think I hit refresh. I'll hit refresh one more time, but you tell me now. I feel like I just fixed the point values. Or anybody let me know if the point value should, everything is 4 points. Yes. Okay. Thank you. And now I'll even admit, great. All right. So this is very helpful for all of us. I appreciate your taking this time with me. Again, hopefully this is to all of our benefits that this is reducing surprises for Wednesday night. Okay, cool. Thank you. Okay, great. And you said I didn't even count. It doesn't count on my side. You're saying there's actually 25 questions. That includes great. Thank you, Ruby. Then that includes the very last one. So I will encourage you. I don't want to on the last one, do try to go to town. Okay. It is, well, you'll see when we get to the end, but do take the last one a bit seriously. Don't be stressed about it, but the more you can give me on the very last one, and it won't be the last one on Wednesday night, but the better. And also just last thing, just note, what's weird about this is this, I've done this before too. I just want to make clear also, many of my weird methods or this and that, it is meant to be not a trick. It's meant to be compassionate. It's meant to give you the benefit of the doubt the same way I hope people give me the benefit of the doubt or whatever, right? But the reason all these systems I think work, my grading systems, my testing systems, is that yeah, most people can end up doing very well if they're trying or they're, ethical, etc. But I just want to remind you that part of the reason that I never get fired for only giving A's or something like that is that there are always some people who don't get A's or even who do get D's or F's for not doing anything at all, right? Why am I bringing that up? And some of them might not be in the room right now, like I've mentioned before. And I don't mean that in a mean way, but I just want to remind you one last time that a lot of why in the end, I hope that you will have learned physics and why this will be a legitimate thing that you will have earned the right to say, I learned some physics and I got an A in physics or whatever, is that you will have done things that are not automatically doable by everybody just for having started the class. You're going to get a good grade and do well on this because you will have survived this whole enterprise. And some people will have not, if you, right? Why am I saying all of that? Is to remind you that hopefully by the time we're done today, I will have made, if you're paying attention to all that, then hopefully, yeah, this final exam should almost in your mind maybe be like almost a joke, not a joke, but like not your most stressful experience. Hopefully it'll be straightforward. You'll feel like you're just like checking off the T's and the F's based on what we did today and then moving on in your life. But I do want to warn you that that will only be possible if you do actually, like, if you hang in with me, right? Like I'm just trying to say this one thing. Each question is worth 4 points. There's 25 of them, right? Just to remind you, like if my mother took this thing or even got together with all of her friends and they all talked about it, and even if they went on the web and stuff, if they haven't been in this class for all semester, honestly, even if like this test obviously does not exist on the web, like Chegg doesn't have this test or whatever. Even if I know from experience that even if my mom and all of her friends got together, talked about these questions and went on the web, they'd still get just enough questions wrong, right? All they would take would be like to get like 5 questions wrong, like 6 questions wrong, and they'd be in the 70s, right? And that would happen if they didn't even know how to look up these questions, or they didn't know what they were looking up, or they didn't know how to read the answers on Wikipedia or in Chegg or whatever. I'm not trying to scare anybody. I'm saying like the thing is, you will take this test at the end and take it seriously, and it's a guaranteed 100 only if you do stick with me today. I guess I think you know what I'm saying. But so do take it seriously. And then let's all assume that all of you who are still standing today, somewhere in all the stuff you've done this semester, will find a material for you and you'll get an A. But you know, when you fill in these answers, well, I guess here's the last thing I'm really trying to say. One thing is, it is a Google form. It is a Google form. So once you fill out the answers and you hit on the real thing that will be posted Wednesday is a Google form. So once you hit the answers and hit send, then that's a lock and that's what you've turned in. So do please be careful. Like, yes, talk to one another, but talk to one another, that those of you who are in the room right now, sure, help each other when I'm done, replay the video, see that it makes sense, blah, blah, blah. But don't hit send until you're ready, because you wouldn't want to just lose a bunch of points just for some careless thing or blah. Okay, you get what I'm saying. Okay, I think you get what I'm saying. Okay. So we're going to start doing physics now, I think. So does everybody clear what's about to happen? Like, can we get one last electronic thumbs up that I'm now going to do physics? I'm going to try to talk about, great. Okay. Thank you, Ruby. Thank you, Althea. Thank you. Oh, wait. Oh, thank you, Manoj. Thank you, Alyssa. Oh, Antonique's question. Oh, wait. Yeah, Antonique's question is a good one. For the last question, I will probably have to make, that is a good point. I have to look, if Google Forms doesn't give you enough room, which I don't think it does, I will probably have to make a separate portal in Google Classroom where you'll just give me, I will make a separate portal where you'll just give me, you like as though it were old-fashioned homework or whatever. You'll just take a blank sheet of paper, and scan it in and upload it. And I am looking for like a sheet, like a half a side of a page to a full side, something like that is what I'm looking for. But yes, you're right. I'll probably, I believe, have to make a separate portal for that. I'm glad you asked. It's a good question. Does that make sense, Antonique? I just want to make sure I've in. Yeah. Okay. Thank you. Great. Okay. So I got the thumbs up, right? So you're saying, so we're ready to go. I'm going to assume, I know people got cut off because I was answering that question, but I'm going to assume you're all ready to go. I'm going to start now talking about physics. I'm going to, again, I'm not literally going to have the questions up on the screen. I'm going to have other things up on the screen. You can tell me if you've lost where I am or whatever, but I'll tell you right now, I will tell you that where I'm going to start talking. Oh yeah, I basically am going to start talking at the beginning. I'm just looking at it again. Okay. I'll tell you right now, some of the questions like work and path and growth come from the beginning of the semester. If you feel like we get to the end and I haven't answered them, you can ask me, but I feel like some of them I need for this discussion, but we talked about a lot at the beginning of the semester, so I might sort of blow past them, but okay, I think you see what I'm saying. Okay, so here we go. Okay. so today is today. Here we go today. Okay. Okay, here is my point. All right. The subject that we've been in the middle of for the last couple of weeks, where we've been is the subject of fields, particularly electrostatic fields, also to some extent gravitational fields. Here is a picture right here on the board is a picture, a very rough sketch of the field lines from a positive point source of electrical charge. That is in other words, like a proton. Plus Q, the point in the middle of the page, stands for like a proton sitting there. It creates electrostatic field. Those lines being drawn out from it are the field lines that represent the electric field everywhere in space created by a point source of charge, such as a proton. Now, I want to back up and remind you like what the meaning of this is, why we care, what it is that we're believing when we say that. So to back up for a second, remember, and here you'll see at the beginning of the questions, you'll see what I'm about to say in a second. Remember that a force is always an interaction between two objects. I push or pull you, or you push or pull me, that's a force. And it causes acceleration. The first kind of forces that we all learn about in physics 203, we know that a push or a pull is happening between two objects because we see the two objects touching. We see them making physical contact. Like when two surfaces rub against each other, we call that a frictional force when they slide against each other. When two things pull on two ends of a string, or when one string pulls on a fish or something, we see the string touching the fish and we call that force tension, right? When one surface pushes against another surface like this, we call it the normal force. But then we start noticing in physics that some forces, some push or pulls between two objects seem to be able to happen without touching, seem to be able to happen through empty space over distances without limit. The first force we ever see like that is the gravitational force. It seems like the sun can pull on the earth without touching it. It seems like earth pulls bricks and stones and everything to its center without touching those bricks or stones or whatever we drop, right? And so gravitation is a force that seems to happen fundamentally. As long as points of mass exist, they seem to be able to pull on each other without touching, without doing anything. They seem to be able to affect each other through empty space, through whatever distance you want. The farther the distance, the less the force, but no matter how big a distance you pick, there's still some gravitational force that seems to be acting between any 2 points of mass anywhere in the universe. We call that a fundamental force, or we call it action at a distance. Another thing that turns out to be just like that, which is really our focus here in the class, is protons and electrons, bits of charge. Bits of charge seem to be able to pull or push each other without touching through empty space, through whatever kind of distance you can imagine. Bits of charge do this same fundamental action at a distance thing that bits of mass do, only bits of charge that can do it in a pulling direction or a pushing direction. That is, as you know, charge comes in two varieties, positive and negative. I'm going to write something here. But so gravity, the gravitational force between any two bits of mass and the electrostatic force between any two bits of charge seem to have one major thing in common, which is that they both act over a distance, over empty space without touching, and over space of any size that you want to imagine. They have another thing in common too, which is that they are both they both have the same math. They're both inverse R squared forces. I know this is not a question. I'm just saying this. You won't find a question to actually ask this, but you probably should. They're like gravity. The gravitational force is F equals GMM over R squared. The bigger either M and the smaller the R between them, the harder they pull on each other. And that big G is just a constant of proportionality that just makes the units work out, right? So that so sidebar, you'll see how this relates. It's not a sidebar. This is not a question, but you'll see how this relates to a question in a moment or two. If you ever literally want to numerically calculate the gravitational force between two masses, you need to know how big each mass is, M1 times M2. You need to know how far apart they are, R, and square that and divide. But you also need to know this number called the universal gravitational constant. I mean, you don't need to memorize it, but you need to have it, look it up or whatever, and multiply everything by that big G number. If you want to get an exact number of newtons that one object is pulling on the other. Similarly, if you want to know how hard one proton is pulling on an electron or how hard a proton is pushing on a proton, you need to know the charge of each one, Q1, Q2. You need to know how far apart they are, R, square it, divide. And then you need to know a constant, a universal constant known as the electrostatic constant. You'll see in a minute, this is about to relate to one of the questions. So you need to know a constant much like the G number. Sometimes it's written as K. You'll see if you scan down the questions, I'm skipping a little bit here, but if you want to calculate that exact force, you either need to know the number K, which is 8.99 times 10 to the 9th Newton meter squared divided by Coulomb squared. You need to know it as a constant of proportionality to make the numbers actually work out and the units actually work out correctly. Like without that number, you can get a sense of what's going on. You can get the proportionality, but you can't get the exact answer. Or you need to know the number that K is actually really based on, a number called epsilon naught, which is 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. K is really based on this number epsilon naught. K really happens to be 1/4 times pi times epsilon naught. You need to know one of those numbers if you're doing a calculation to really figure out electrostatic force, or as the question says, electrostatic field. I'll make that distinction in a second. But I'm telling you right now, one of those questions says something like true or false, the electrostatic field depends on neither K nor epsilon naught. The exact question, I don't remember the exact wording, but it's in front of you somewhere. One of the questions says, true or false, the electrostatic, if you want to know the numerical exact electrostatic field due to something, it depends on neither the number K nor the number epsilon naught. That is false. You need to know one or the other. You don't need to know both because they're both related, but you either need to know K or better, you need to know epsilon naught if you actually want to know the electrostatic field caused by a charge. So that's one of the questions. I don't remember which one, but let me say now, if you're really paying attention to me right now, you might be noticing, wait, Yaverbaum was talking about force for a while, and he was addressing like the first question about you need 2 bits of mass to make, there's some question at the beginning, like to have a gravitational force, you need a minimum of 2 masses or something like that. That's true. To have a force, you need 2 objects. So I was talking about force. Then I got into this inverse R squared thing. And then but then there's this weird thing where I said this picture was the picture of a field, and this, no problem. Got you. No problem. But thank you. So I was talking about force. I answered at least one of the questions for you, the early ones about force. But then I said that this picture was about field. And then I did this like confusing sidebar where I was like, oh, in order to calculate the field, you need this number. And that's one of the questions. And I got it right. If you're still with me, what you might be thinking, I almost hope you're thinking is, wait, he was talking about force and then he was talking about field. Hold on. Are they the same thing? Is he saying that that's the same thing? Do I not have to worry about the difference between those 2 words? Or is he just being confusing? Let me tell you now, there's a deep relationship between force and field. There's a deep relationship, but there is a difference. And it's part of why I'm here today is to try to make sure we're straight on that difference. Let me tell you, if you look at what I think is maybe the second or third question in the true or false, the difference is this. A force is something one object does to another. A force is I push or pull you, and therefore by Newton's third law, you push or pull me. Okay, a force is an interaction between two actual thingy things, two particular objects. But since some forces, such as the gravitational force and such as the electrostatic force, since some forces seem to be able to happen through empty space without any touching or activity at all, since some forces just seem to happen as long as the objects creating them exist, and even more to the point, since these fundamental forces like gravity and like electrostatics seem to be so numerically precisely based on the numerical precise descriptions of the objects doing them, i.e. what I mean is like the sun pulls on the earth, or even better, the proton pulls on the electron with an exact number of newtons that is literally determined by the universal constant, but also determined by how big one charge is, how big the proton is in charge, how big the electron is in charge, and literally how far apart they are, what the separation, the displacement R is between them. Since the exact sum number of newtons seems to be determined specifically, precisely by the distance between these two objects and the size of these two objects, that means if either one of them moves at all to another location or gets bigger, gets like attached to some more charge or something, or gets smaller, the force between them seems to change, right? Like, so if a proton's pulling an electron, it pulls within an exact amount that's based on how far away the electron is. If the electron starts getting pulled in and starts getting closer, the proton now pulls on it harder, like F equals 1/4 pi epsilon naught times Q1 times Q2 over R squared. If the R changes, the whole F seems to change. So that means to us that what that raises is this really weird, almost mysterious truth, which is, wait, this proton pulls on this electron with an amount of force that is determined by how far away this electron is. And it's so precisely determined by that when the electron gets closer, the proton pulls harder. That's got to mean that somehow the proton receives the information of where the electron is, right? I mean, literally, I know I've said this before, but just let me make this as clear as I can. One of the great original mysteries of physics to Newton and to the people that came between Newton and Einstein is, oh my God, how is it that a proton over here knows precisely how big and how far away an electron is over here, such that to the point where even if the proton starts getting closer, the proton updates its pull. It pulls harder when the electron's closer. How does the proton get or have the information describing where the electron is if there's nothing in between the proton and the electron to deliver that information to the proton, right? So I'm saying with forces that happen at a distance, such as gravitation and electrostatics, they seem to be so based on information that seems to be somehow describing points in space over here, but accessible to points in space over here, that what we say is, okay, something's going on. There's something in between those two charges. It's empty space, I get, but there's got to be somehow information deposited and transmitted between objects, even through empty space. So whenever these fundamental forces are acting. So what we say is that for every fundamental force in which we believe, there's first and foremost a fundamental field. We say, instead of saying that the proton pulls directly on the electron, we say that if there's all this empty space, if there's a blank universe, if there's nothing, and we deposit one proton into the space of the universe, if we deposit, if one proton comes into existence in space, before anything else happens, or without anything else happening, that proton creates a field, which is this diagram right here. It creates a field. A field is the collection, and here comes a question. This is definitely one of the questions you'll see. A field is a patterned collection of okay, sure. Thank you for coming. Absolutely. Okay, cool, got it. Thank you. Okay. But hear this one thing for you. A field is a patterned collection of information sitting at any and every point in space. That's what a field is, and that's what these lines are meant to represent. We'll go back to that in a second. But a field is, so a force is something that I do to you. A field is something that I do to space. A field is the information describing how big I am and where I am, deposited everywhere in space, so that if and when some second object comes along, some second charge that we might call a test charge, if it comes into space, it lands at any point in space that it lands, that it's deposited, it's already sitting in like this sea of information. It's sitting right on some sort of vector or some sort of line that tells it precisely how many newtons of force each coulomb of positive charge of it will be experiencing if it sits there. The field is the force waiting to happen, waiting to be exerted on each coulomb of positive charge that could be deposited at any point in space. The field is, if force is measured in newtons, field is measured in newtons per coulomb. It's how many newtons would be exerted on every coulomb that might hypothetically be at any point in space. And the field has magnitude and direction. It tells every coulomb of positive charge that could be anywhere in space in what direction it will be pushed or pulled, and how many newtons of force, how hard it will be pushed or pulled. Okay, and that's what these lines represent. So I'm ultimately saying this. I'm just going to add something to this picture here. Hold on a second. Okay, up top, I'm writing it the sort of fancy way with vectors and with the full 1/4 pi epsilon naught. Bottom, I'm writing it just the magnitude, the less fancy way. There are two ways of, one is a more complicated, more complete way of saying it. The bottom is the less complete, less proper way of saying it. But what they're saying there is that's the field. This is the field due to 1 point charge. Notice there's only one Q in the numerator. It's not Q1 times Q2. It's just Q. So again, so this is also one of the questions early on. A force is an interaction that requires two objects. A field is the sea of information that is created by just one object. And then if any other, and the object that creates the field we call the source. The object that would experience force from that field we call the test object. The source is the creator of the field. The test is the receiver of the force from the field. Okay, so their field is related to force, but field is
what an object does to space. And field is only relevant to fundamental forces like gravitation, or particularly for us, electrostatics. Like there's no such thing as a friction field, or there's no such thing as a normal force field or a tension field, because all those forces happen by touching. So there's no, but these forces that don't happen by touching involve fields. Okay. So this is the picture of the field lines from a point charge. The lines, like we said yesterday, or I mean, like we said last week, the lines are a representation, just like and they're like vectors, but they aren't vectors. They represent what's going on in space. These lines supposedly go on forever. I mean, all field lines go on forever unless they hit a negative charge. Notice they're spreading out equally in all directions from that positive charge. What they're trying to say is direction and magnitude. The tips and tails tell you the direction of the force that you would experience if you were 1 coulomb of positive test charge anywhere in space, right? So wherever you are, you'd be shoved out. If you were a positive test charge, you'd be shoved out. You'd be repelled by that positive source creating the field. And you could tell how hard you'd be pushed out by the density of these lines. Like notice the closer to this point charge, the more in the inner circle we are of this picture, the lines are very tightly bunched together. They're very dense. There's a lot of them. That indicates high strength, high magnitude of field. As you get farther and farther away, the lines get farther away from one another. They get less dense. They get less crowded. That indicates weaker field. The field gets weaker as we get farther away. It's inversely proportional to r squared. R is the distance away from the source. So the way we read these lines, the lines indicate magnitude and direction. Their tips and tails indicate direction, and their density of lines indicates magnitude. And that's how you read the picture. If you, okay. Yes. Wait. Yes, okay, I'm going to read. There's a question in the direct chat. I won't say the person's name because it's direct chat, but it's great clarification question. I'm just going to read it out loud. Someone's written in the direct chat. So if space is like a sea of information, then to establish an electrostatic field, a charged particle or multiple charged particles must exist. Okay, I totally want to unpack that. That's a great thing to write in the direct chat, and please submit it for points. First of all, I'm totally agreeing. Yes, like to make electrostatic field, we need a charged particle, or like he or she said, multiple charged particles. Like you need charge to make electrostatic field. If you have 1 point of charge, the field will look like this picture. If you have multiple charged particles or a bunch of charge like formed together in some sort of shape, it'll make a more complicated picture. We're going to look at those in a moment. But yeah, to make field, you need charge. And but now the first part of what he or she said, the field is a sea of information. Space itself is blank. Okay, space is literally like space. It's the same in all directions. It's the same in all subspaces. Space is just, not only is space itself like nothingness, but space itself, like empty space. I mean, if you didn't put any objects in it, it would be emptiness, it would be nothingness, like literal space. But here's a key point about it. It would be sameness. What the real essence of space is that it's like the definition of sameness. Any two regions, a cubic centimeter of space from right here is literally indistinguishable from a cubic centimeter of space taken from the Andromeda galaxy or something. Like you can't, there's no markings. You can't tell the difference if I took a chunk of space, a cubic millimeter from the Andromeda galaxy or a cubic millimeter from here. They literally are the same in every way. Similarly, this direction in space is indistinguishable from that direction in space. In pure space, there's no such thing as left, right, north, south, up, or down, right? So the first idea is called homogeneity of space, and the second idea is called the isotropy of space. I'm just trying to say right now to riff off this question for a moment. Space is sameness, pure symmetry. The minute we put anything in the space anywhere, the minute we put one bit of charge, one point of charge over here, then now we've interrupted that sameness. Now we have a little difference. Granted, it's very little, but we have this little point of charge over here. Immediately, or I shouldn't say immediately, but that point of charge will now create a sea of information. Like the space was blank before, but now a sea of information will go everywhere in that space, and it'll go in the form of lines that will come out radiating equally in all directions from this point. The lines will radiate, and I don't mean they're literal like charcoal lines, but I mean something resembling infinite arrows will come out in all directions from this point and spread out everywhere, so that and all the arrows will be like the same. They'll be infinitely long, and they'll go out in all directions because space everywhere is the same. But they'll do all of that from this one point. So the one asymmetry in these arrows will be that they all converge on a point. This is very important. I mean, so there's this sea of information will now exist kind of like in the shape of like a starburst or a sunshine. And it's a sea of information, as the person says in direct chat, in that anywhere else in space now, there's these rays now that actually tell us, like tell in the non-human sense, but if you happen to be located somewhere, anywhere in space, if you were a positive Coulomb of test of hypothetical point charge anywhere in space, you could, where you were, the rays would be a certain amount of farthest. You could tell by how, you could tell that the rays were going like this, you'd be shoved out like that. And if you trace them back in your calculator, if you trace them back, you'd be like, oh, there's a proton over there. And you'd be shoved, you wouldn't be shoved so hard. You'd be shoved very hard if you were down here, but up here you wouldn't be shoved so hard. And you could tell that because the rays would be diverging a lot. They'd be very spread out where you are over here. So of course, this is all like a metaphor, just like vectors don't like literally exist in space, like as charcoal lines. These field lines don't, they do exist, but they don't literally exist as like charcoal or something. But the point is that the minute there's one proton over here, it sends this pattern of rays out everywhere. And the pattern of lines tells everywhere else in space exactly what's going on. From the fact that the lines are pointing in a certain direction and spread out to a certain extent, anywhere in space, we could tell, oh, there's a dot over there, right? So yes, I'm agreeing with the direct chat person that you won't get these lines at all until a point of charge or multiple charges exist. But once you get some charge somewhere, they create these lines. The lines are, and again, I don't care if you don't literally like, well, I mean, I do care, but it's like the equator. Okay, we all understand what the equator is around the center of the globe, right? I mean, it's very meaningful, the equator. It's very meaningful. We don't literally think, and it really is there. It's just it's not charcoal. It's not concrete. It's not actually a wall or something, but it is a real concept, the equator. These lines are like that. And just like if you stood at the equator, you'd be rotating at 1,000 miles an hour. But if you stand anywhere else besides the equator, you're rotating slower than 1,000 miles an hour. Like it's meaningful, it's real. It makes it, or literally, even let me give you a quick, better example. How is the equator real? The equator is real in that if you literally go to the equator and you literally go to the beach on the equator and you literally lie down on the beach and you literally lie down on the beach, on the autumnal equinox or the vernal equinox, if you like lie down on the beach on the actual moment of the equinox on approximately March 22nd or September 22nd, and you're on a beach on the equator, the sun will be directly over your head. Like you stare up to the sky, the sun will be at the top of the sky. It'll shine down on your body. You'll get the best tan or whatever, right? Or you'll have to close your eyes because you're looking straight up to that sun. And if you go anywhere else besides the equator at that moment, noon on the equinox, the sun will not be directly over your head. Like that's only true at the equator at that time, at that space. It's meaningful, it's real, but you won't see a line in the sand that says welcome to the equator, right? It's real, but it's not actually a physical marker. Same thing with these field lines. These field lines, they're not drawn in space, but they are real. What they're really saying, like the direct chat person said, is the field lines are our way of picturing that the minute there's a proton over here, somehow, some very real way, the information describing that proton's strength, electrical strength, and that proton's location does exist over here. Somehow, space over here has access, is aware of, knows the information of the existence of that proton over there. And very precisely, like if we put another proton here, it will be pushed in a certain direction with a certain number of newtons. Our picture of the field lines is our picture of that. The more the field lines are spreading out, the weaker the field. The orientation of the field lines is the direction of the field. Okay, and I'm going to go on. So it's a great question that was in the direction. Okay. No, thank you. Thank you for the question. It's great. Now I'm going to go even on with the question. Like, and I know I'm a little bit, it seems like I'm off page right now, but like I said, this is why you're following. I mean, you'll see more and more of the questions are going to start getting answered. I mean, the TF questions, but the more you understand this whole thing, the more you'll really understand the TF questions, obviously. So what I want to say now, I'm going to switch screens for a moment. I'm going to be expanding. This is not a digression. This is like what we have to talk about, but I think you'll find it also does relate to this direct chat person's great question. I'm going to switch screens now and remind you of a couple of pictures that we looked at on the overhead projector, in the classroom. I want to remind you now of what the field line pictures the field line diagrams look like when we get slightly more complicated things causing them. Like the direct chat person said, who really deserves to have his or her names, but I won't. But anyway, great person who said, anyway, like this is the simplest possible picture. Okay, this is the simplest situation. This is what happens when just any one point of charge creates field. But of course, we could have 2 points of charge next to each other, or we could have 3, or we could have 2 points of charge that are of opposite charge, or we could have like a whole stream of charges like so close to each other that they make like a line or something. The more complicated the picture of the more complicated configuration of charge we have, the more complicated the field lines are going to get. Again, the field lines tell space over here what's going on over there. So let me switch screens for a minute. Bear with me for a second so I can show you some other pictures I want to. Yeah, bear with me for a second. Sorry. Oh, did I lose? Okay, hold on one. Bear with me for a second. And obviously you could do this on your own too, but here we go. Okay. Sorry. Give me one more second. I'm just. Here we go. It's coming. Okay. Okay. Now, you've seen this before, but let me just make clear. Like the fact is, field line pictures can get more and more elaborate. You have the three examples here, on the screen. And this is just Google Images. This is nothing like you could find a million of these on your own. And there's simulators, which are fun to play with. Maybe we even will, but what's going on the screen? But I'm saying there's nothing like, this isn't like some insider physics teacher's like web search. I mean, it's like totally, anyway, what you're seeing on the screen, diagram A all the way to the left, that's a positive next to a negative. Diagram B is a positive point source next to a positive. Oh, and and diagram C is a positive next to a negative, but the positive is much stronger. It's like the positive might be like 50 coulombs of positive charge, and the negative is like 1 coulomb of negative charge or something like that. I think we've mentioned this before. Now, these are just examples. And these pictures, let me remind you, these pictures are the field line diagrams due to these particular examples of source charges. These pictures don't tell you what one charge in the picture is doing to the other charge. They might look like that's what they're doing, but that's not what they're doing. What they're telling you, this is like the direct chat person's question, what these pictures are telling you is what the pair of charges, the whole group of charges is doing to the rest of the universe. These pictures are telling you what would happen if I took, like, can you see my arrow? Yeah, you can. Okay. If I watch the cursor arrow would represent like a test charge. It would represent 1 positive coulomb of hypothetical point charge, like one little hypothetical test proton that could be anywhere in the universe. And if it landed, like, say, right here in that first picture, then what the diagram is trying to tell you is what would happen to that third party, to that test charge of 1 coulomb, 1 positive coulomb, as a result of the positive and negative that were already in the universe, right? So the positive and negative together are creating this one big field that would be affecting some third party, some test charge. And the idea is if my arrow, the test charge, or my arrow were right here, like at the top of that, at the top of this curved field line, right where that red arrow is, the whole idea is that at that point, I would be shoved to this way, to your right. I would be shoved to the right. Why? Because I'd be shoved to the right, literally to the right, even if I was right here. Why? Well, if you think about it, the positive guy would be pushing me up and to the right. Like positives always push out on positives, and we always assume that the test charge is positive. So the positive source would be pushing me up and to the right. It'd be repelling me up and to the right. The negative, which is an equal but opposite charge, would be pulling me, right? Because I'm positive. If I'm the test charge, if I'm this little black arrow right here, I'm positive. So the positive source would be pushing me up and to the right. The negative would be pulling me down and to the right, right? So the up and the down would cancel. They'd be equal because I'm equidistant between the two. I mean, I picked this point on purpose. The up and down would cancel, but the horizontal would reinforce. I'd be shoved very hard to the right because the positive source is pushing me to the right. The negative is pulling me to the right. So they're both agreeing. They're both pulling me to the right. So I definitely go to the right, but they're disagreeing in the y component. So the y component would cancel. You so far see what I'm saying? So that's what partly the field line is showing me, like right at that point is showing me how the vectors already added up. Like it's doing the math that you I shouldn't say that you worked hard to do to get the 14 points. It's just giving me the vector sum right at that point and saying, okay, direction wise, you'd be shoved to the right. Magnitude wise, like how hard would I be shoved? Well, evidently, if I were up here, I wouldn't be shoved that hard. The field is kind of weak up here. I'm far away from the positive and I'm far away from the negative. The field would be kind of weak up there. It'd be weaker than if I were over here, let's say, or over here or over here. How can I tell? Because the lines are getting more and more dense as I get closer to the positive and negative. You see what I'm saying? So I'm saying that this pattern of lines, this really intricate, beautiful pattern of lines is a way of showing what's going on at any single point. Any single point, we can tell direction from the arrowheads, and we can tell magnitude from how crowded or how dense the lines are. Okay, hopefully you can sort of understand that. If you don't, please put a question in the chat. If you don't, and I'm not saying, and again, you could tell you've got I'm going to get back to the true false, I'm about to answer the next true false. I don't know if it's literally the next, but I'm about to answer another one of the true false questions. What I want you to see is that I'm not going to make you draw a whole bunch of these pictures. They're a little bit hard to draw until you get used to them. And I'm not going to make you read a whole bunch of these pictures. I want you to see the pattern, the larger takeaway of how the patterns of the lines work in these pictures. Here's what I'm trying to say. No, and it's about, as I keep saying, it's about to be one of the questions. I'm saying that if you look at these three pictures, they are intricate, they are elaborate, they might even be intimidating, they're very fancy, right? And as you can tell, and they're fancy, but they're not even that, they're based on not particularly complicated sources. Like the source here in diagram A, the source is a dipole, an equal positive and negative, like a pair of equal and opposite charges. I mean, that is definitely more complicated than just 1 point charge, but it's just a pair of equal and opposite. Then here is a pair of equal non-opposite. By the way, notice right in between the two, there's no field lines at all. There's no field because the left guy's pushing you to the right and the right guy's pushing you to the left. You see, it's just all the lines are, but whereas if you're up here, you're being shoved up because the left one's shoving you right and up and the other positive is shoving you left and up. You see what I'm saying? Like the pattern of the lines is a result of what caused them. And here, even what's caused them is pretty simple, but it's just a little bit more complicated than 1 point. So the lines are a little bit more complicated than the starburst that we have from just 1 point. Then when we go over here, the lines are starting to get kind of complicated now. Because we have the most complicated source of all here. We have an asymmetric pair, a strong positive next to a weak negative. So it makes this comparatively complicated diagram. Now you'll never have to draw a diagram that complicated, but here's what I'm urging for you to see. I want you to see that a couple of things. I want you to see that no matter how complicated these pictures get, they're always very patterned, right? Every one of them has a definite pattern. None of them is random at all. And none of them is crazy. Like once you look at it, they have some sort of pattern and the pattern absolutely echoes whatever the pattern is of the charges that cause them. Let me be more specific about that. What I really am trying to say in this, I keep saying this, but this is about to be one of the questions. All the lines always have a certain amount of symmetry to them. We start with the idea that space is totally symmetric, that if there was nothing in space, there'd be no lines at all. Then if we put one little dot of charge in space, we get lines that are as symmetric as can be given the one dot. If we put 1 point of charge in space, we get lines that are as symmetric as they could be, given that they all come from that one dot. What I am trying to say right now is a field line picture, here's one of the questions, is only and is exactly as asymmetric as the source that causes it. That is definitely one of the true false questions. I don't remember if I wrote it as true or if I wrote it as false. You can even put in the chat if you found it. You can help your colleagues. I don't care. I mean, I'm all for it. But I'm saying right now, it's a really important idea. It's kind of an obvious idea, but kind of not. Like, I don't know if you think it's obvious or not. But I'm saying if you look at these pictures, some of those pictures are like, if you look at this picture, they're getting more and more elaborate, right? But they always have some symmetry and some asymmetry, like some not symmetry. The asymmetry that a picture has is is the indication of exactly what's causing it. The picture shows what's causing it by revealing that asymmetry. Let me put it again, that is definitely one of the questions. I'm trying to say that a little test proton over here, like that found itself over here in space, just if it knew, I mean, this is all, again, it's like the equator. I'm not saying that we're like literally drawing these lines, but I'm saying these lines exist for all intents and purposes in space. And if I were right here in this point in space, by seeing the pattern of lines over there, I would be able to know, oh my God, there must be a positive here and a negative here. Like literally, I would know that there's a positive and negative from this pattern of lines. And I would know where they are because the lines come from there. You see what I'm saying? There's a one-to-one correspondence between what's causing the lines and the pattern of lines. If you see, once you're in the pattern of lines, you, a point in space, can tell what's causing them. Therefore, this pattern of field lines is the mechanism, it is the sea of information. As someone said so well before, these lines are the sea of information that wouldn't be there if there weren't rocks or whatever causing this sea to exist. But the pattern of the water, and it is still water right now, but the pattern of this sea literally is the mechanism by virtue of which this point in space over here knows what is existing, how much charge and what shape of charge is existing over there. This sea of information is the way that one point in space has access to what's going on in any and every other point in space. Okay, that's the idea of the field lines. And again, the takeaway, I know I'm dwelling on this because you need it for the rest. The rest of what I say will, like, big takeaway of today, number one, I'm just going to say one more time. I know it only answers like maybe one question, but all the rest of the questions are sort of based on it. Or the understanding is based on it. What I want you to see is that field lines convey information, okay, of what field lines convey information to one point in space of what's going on at every other point in space. The way they do it is through asymmetry. I want you to know, I want to say it one more time, a picture of field lines is always as symmetric as it can be. It's as symmetric, patterned, smooth, simple as it can be, given whatever asymmetries or complexities there are to the thing that's causing the field lines. Field lines are only as complex or as asymmetric as whatever's causing the field lines. That's, in fact, how they do their job. Put one last way, field lines are exactly as asymmetric or complex as whatever's causing them. So that's how they, again, remember, if there was nothing in space, then there'd be nothing in space. If there was nothing in space, if there were nothing in space, if there were no objects, no charges in space, then there'd be no lines in space. The minute we start having charges in space, we have these lines. The pattern of the lines tells the rest of space what charges are assembled in what fashion, where. Okay, so the pattern of lines are how all of space knows that there's some pattern of charges somewhere in space. And the more patterns we put in, the more we affect the lines. Okay, and again, I'm not telling you that, because I remember honestly, Nick, I don't know if Nick is still with us today, but I remember he asked about this last week. Totally fair. I'm not literally trying to tell you to like literally believe in charcoal lines in space. But I'm telling you what you do have to believe in, or I mean, what seems to really happen in space is somehow when something exists over here, when a bunch of charge exists over here, somehow things over there get pulled or pushed in a very particular numerical way that's dependent on what is over here and how it's shaped and how strong it is. So these lines are just our way of understanding how it is that the information describing what's going on over here is accessible to any and all points of space over there. I'm not telling you that you like literally have to swear on your like grandmother's grave that like literally there are these lines literally in space. But what you have to understand is these lines are our simplest, best way of understanding, of modeling, of representing the fact that there is the information everywhere in space describing what's going on everywhere in space. Okay. That's what I'm saying. Just like vectors or anything else, or graphs. Like, you don't literally believe that graphs like exist, but they represent what's going on now. So symmetry and asymmetry are the key here. Oh, and there's something in the chat, so forgive me. Hold on a second. And we're doing fine on. Let me just see the chat. Sorry. Oh God, great. Sorry. I sound like I'm in pain, but I was probably worried. Carly's question in the chat is fantastic. I mean, all these questions are fantastic. And honestly, again, I don't know if Nick is still listening or still here, but I sort of gave him a hard time almost for his question last time about that, but it was a great question. And I hope maybe I've addressed it now. And it's a tricky question, but Carly's question, she says, for both field and force magnitudes, is it true to say that the length of the lines doesn't matter and only the pattern density of the lines matters? Yes. Precise amundo. Like I think I couldn't have put that better myself. Like, I can't even tweak that. Like, that's exactly my point. Right. And well, I'm going to add to it. I mean, but I totally agree. And I agree that it's important takeaway. And if that helped anybody else, if my words didn't make sense, but those words do, go with those words. Because what I'm trying to drum in, and you'll see why in a minute, like, I have to use this for the next hour that we're together. And also I would recommend, if I hate to keep talking about, but this class is longer than the other two classes I had this week. So this video will be longer. So I think it might be even more helpful for the final. So if any of you as friends in the other classes and want to recommend to them to watch this video, like, it might, whatever. I mean, I think we're having a clear discussion here as a result. Anywho, Carly's point is, oh yes, like, these field lines all represent vector sums. They're originally built from vectors. They're like, we could originally imagine that at every point in space, there's a little vector showing us how hard we'd be pulled or pushed and in what direction. But the vectors end up getting so hard to draw. There's so many of them and they're everywhere. And we have to do all this vector addition and stuff and add them up and cancel out components and everything, like y'all did for 14 points, that in the end of the day, we have this better method of connecting up all the vectors and drawing these field lines. Again, notice these field lines, they're based on vectors. They indicate the same type of information that vectors do, which is magnitude and direction. But indeed, as Carly is observing, these things themselves are not vectors. These lines curve and bend. And unlike vectors, exactly as Carly's saying, these lines, they go on forever unless, and they come from forever unless they happen to start at a positive or land at a negative. But the rule of these lines is, if they're going to start at all, they start at a positive. And if they're going to end at all, they end at a negative. Other than that, but anywhere you see, like in these pictures, like here, and you see, by the way, there's a very clever thing that Google, or that, I didn't even think to do for years. You notice how on all these line pictures, hold on, let me just get rid of the chat for a second. You notice on any of these pictures that we're looking at, and some of those are intentionally false pictures, but any of these pictures, well, actually not any, well, actually, let me go. Okay, sorry, let me go back to these. The smart thing that they do in these pictures is they put the arrows like in the middle of the lines instead of at the end. I actually never even thought to do that. They're doing that on purpose to show you that they are not vectors, that the lines don't end at the arrow tip. They only end if they hit a negative. Other than that, you're supposed to believe that they're going on forever. This is just like a slice of space. They're just ending because the page is ending, but they're going off in that pattern forever. And we're supposed to believe that they've given us enough of a sense of the pattern that we can extrapolate that pattern forever. So it's absolutely true. What Carly's saying is that unlike vectors, you cannot infer anything from the lengths of these lines. They don't have length. They only have length when they happen to go from a positive to a negative. So there's nothing to infer there. That's just the space between the positive and negative. If they're not hitting a negative or starting a positive, they're going on forever. So it's Carly's, I'm just going to say it again because it's so important. Carly's absolutely right. The length of these field lines don't tell you nada. They don't tell you anything. What tells you about magnitude and direction is how close they are, the density, i.e. the pattern. So the pattern of these lines indicates to space and to the reader, the pattern of, so great question, truly. And please keep clarifications like this coming. It's helping me help you. And we have an hour and I'm aware of that. And we will move forward. And we will get to the end for sure. Oh, yeah. The pattern of the lines indicates, represents, models the pattern of the charges causing the lines. Again, what's the whole essence of all this? It's like, how does one point in space over here know what's going on over there? Answer, pattern of the lines. And again, the key thing that I want, you'll see why in like 1 second, why I have to make such a big deal of this is, remember, as elaborate as these lines look, and as intimidating as it might look at first to look at them, like you might look at them at first and think, I could never draw that. I would need like Google images to draw them or something. But it's not actually the case. The truth is, once you get used to this, you start to realize that there's one and only one way to draw the lines for any shape that you're ever given. There's one and only one way to follow the rules and draw the lines, as long as the main rule you follow is, and we talked about this like on the board, last week, there's a couple of rules, like if you're going to start at a positive, if you're going to end at a negative. Lines are allowed to bend, but they're not allowed to cross, rules like that. But then the final rule is, given all the above rules, draw the simplest, most symmetric, smoothest picture you possibly can. That is the field line picture. Remember, I'm saying the field line picture is the simplest, smoothest, most symmetric pattern it can be, given all the above rules. Given, in other words, all the constraints or asymmetries imposed upon the picture by whatever's causing it. That's how the pattern of field lines shows what's causing it. Now, I'm going to switch boards now. I had to keep saying that because what we want to get into here in a moment is the really interesting final last question, which I sort of alluded to, in fact, at the end of last class, I guess, with you guys. What we really want to get to is what happens if the pattern changes. What happens if the universe changes? What happens if we add a new proton to the universe? Or what happens if we move a proton over? In other words, what happens if we want to update this information? Everything we're saying right now, this sea of information we're talking about, it is a sea in the sense that it's like everywhere, but it's like a pond. I mean, it really is like a pond. Like this is all, these pictures are what's happening. In fact, this is part of one question. These pictures represent what snapshots of the universe, of space. They are what the pattern of information looks like at any given moment, given what is in the universe right at that moment. Okay, so I'm going to switch screens for a moment again to make clear, like, pardon me, forgive me. Okay, so, all right, I'm back to, right, so that was one field. Now this, again, this is my stupid sketch of one of what you already looked at. Like, it's bad, it's a rough sketch, but you see, it's that you can tell it's bad, but it's good enough that you could tell I've tried to draw a dipole here, a positive and negative. It's horrible because like I'm a spaz, but it's not impossible to draw. Like I just followed the rule, whatever. Okay, that's a dipole. But then now here's what, okay, this is next picture, which is coming up. Also a little bit muddy, but I want to talk about for a second. Just an example. For some reason, this is a hard picture to find on the web, even though I didn't draw it very well. What this is supposed to be is, imagine a line of static charge, okay? Imagine like that we have a whole row of tightly packed protons, like literally a line of them, like an x-axis of protons, okay? So point, positive point, positive point, positive point, positive point, okay? So each one of them would create field lines that would radiate out in all directions from that point, right? So this point right here would make a sunburst of those rays going out equally symmetrically in all directions. Then the proton next to it would do the same thing, rays out in all directions. But these two protons are next to each other. So kind of like you saw in some of those early pictures, like the proton on this side would cause a line going that way. It would like push to the left. This proton would push to the right. So those two pushes would cancel each other out, and there'd be no horizontal component of field between them, right? We saw that in one of the pictures, right? And then same thing with the proton to the next of it, next to it. In other words, if you had a whole row of protons, all the protons would burst lines out in all directions of space, except all the ones along the x-axis would cancel themselves. And what you'd be left with is a picture kind of like this, although this is a cross section, as it says on the top. If you had a line of charge, just literally a line of static charge sitting still, it would create field lines that would spoke out of it in all directions, spoke, right? Like, in other words, there'd be lines going up, there'd be lines coming down, like the picture shows. There'd also be lines coming out of the page at you that, like, I can't show in that picture, like spiking out of you and spiking in all. In other words, this would be like a centipede with legs going out everywhere. The lines would come out in all directions except for the direction, the axis along which this line was placed. Do you follow me? In other words, one point sends things out equally in all directions. One line, excuse me, let me say that again. One point, one zero-dimensional point would send lines out in all dimensions except none. Like, there'd be no dimension that anything funny would be happening on, because one point is no dimensional, right? It's not asymmetric along any axis, so no axis would be treated specially. It would burst out lines symmetrically in all directions. The picture from one point would be as symmetric as it could be, given that the asymmetry of that one point. What's the asymmetry of that one point? Just the fact that it's here rather than here. So all the lines would come out of here rather than there, right? But if you had a line, like this picture is trying to say, if you had a line, then there's of charge, right? Like a line of protons sitting all really tightly next to each other, all in a line. Then all the field lines would burst out in all dimensions equally, except for that one line. There wouldn't be field lines going horizontally. There'd be field lines spiking everywhere but that axis. I'm just trying to reinforce again, notice that so the lines would be as symmetric as they could be. They'd be symmetric on all axes except one, because the charge is all along one axis. I'm trying to say again, for the 90th different way, that the only asymmetry or complexity there'd be to that picture would be because of the asymmetry or complexity of that which caused it. So if I were ever in space and I saw a sunburst of field lines, I'd know it was being caused by a point. If I saw spikes, if I saw like a centipede, like an insect of field lines legging out, I would know there's a line of charge somewhere. The picture of field lines is as symmetric as it can be, given whatever's causing it. Why am I saying that? Oh, right. And if you really follow me, you'll even understand that if I then had a plate of charge, if I made a big sheet of charge, two dimensions, like an x-axis and a y-axis of charge, then the field lines would all be along the z-axis. Field lines are always as symmetric as they can be, and they will only have whatever asymmetries indicate the asymmetry of the source. Now, here's where it gets, we're about to go to the next, we're about to start flying through the questions now, okay? I had to lay that down because it's conceptually, believe it or not, it's such a conceptually important point that as long as you get it, you'll get all the rest of what I'm going to say. But all the rest of what I'm going to say is going to hang on that point. What I'm going to say next is, okay, what happens if there's a change? What happens if, say, a proton like is there creating its sunburst, right? Its radial field lines. What happens if the proton starts moving across, like starts moving like this? Then that whole sunburst is going to track with it, right? The lines are going to change in space. Like if it starts tracking through space, it's going to start like what was a sunburst over here is now a sunburst over here. And then it's a sunburst over here. The lines are going to shift, right? And we're going to get that pattern is going to start doing something. We're going to start cutting through that pattern, right? If a proton moves across. And if one proton just darts across, there's going to be an interruption in that pattern. It's going to look cockamamie for a minute until the proton settles down over here, and then the pattern will settle over there, right? So something's going to happen to that pattern of field lines that I want to think about. Well, it's sort of hard to track. If I just think of one proton moving across, the whole thing's going to happen so fast. It's hard to make sense of. But let's go a step further. Let's say instead of one proton flying across, or instead of one line of protons sitting there, how about we have a line of protons continuously marching across? What if we have a flow? What if we have, in other words, what we might call an electrical current, like you spent so much time obsessing over in the lab? What if, in other words, I create a situation where the field line picture is changing? Like, what if I start putting protons in motion and bringing them across my field of view so that I start messing so that these radial lines start doing something? But what if I keep doing that? What if I have a continuous flow, a current, constantly, like a long wire that has current, a really long straight wire that has current continuously going through it, so that it's like a river? They're talking about sea of information. What if I now make a river of information so that at any given moment that I stare at it, on the one hand, I see motion. I see that some change is occurring. So some change in these lines must be occurring. But yet, like a river, what if I've set it up, a current, so that it's steady flow, so that it's always flow, but it's always flow? You follow me? In other words, what if I set up a situation where we have changing field, but constantly changing field? This brings us back a little bit to like physics 203, all the time we spent on like constant velocity and then constant acceleration. Always in physics, we're trying to deal with changes, but changes are like derivatives. Once we have a certain level of change, we can back up and say, okay, there's a change there, but the change doesn't necessarily have to be changing. It could be a constant level of change. It could be a pattern unto itself that we can make predictions about, right? Like once upon a time, things moved. We thought that was complicated until we realized, no, they can just move at a constant velocity, and constant velocity, average velocity is displacement over time or whatever. And we can make predictions that even though it was here and now it's there, we're like, oh my God, we could say, well, as long as it moved at constant velocity, we know in an hour where it's going to be. Or, and then we went a higher level in physics 203. We're like, even if a thing is speeding up, that seems hard and complicated, but as long as it's speeding up in a constant way, we call that constant acceleration, we can do things like x equals 1f at squared and make predict, right? So I'm saying, remember, part of the whole background of calculus and physics 203 here is that we can deal with rates of change. Each new rate of change can be like its own constant, reliable thing. So what I'm saying now, bear with me, please, and you're doing great so far, I think, I believe. I'm saying now, oops, sorry. Okay, I'm saying now, this picture that you're looking at here is a line of static charge. It's a different picture from one point. This picture would be spikes of field lines, like caterpillar legs. That follows the same rules as one point of static charge, but it's a different picture, right? If now I want to ask you, and again, for those of you, I mean, I know many of us are like, we have to come in and out or make the subway. So definitely just please watch the video for like any points that you might have missed up with tonight, because it all, I think, fits together. But anyway, I'm saying if that picture that you're looking at right now is just a line of static charge, a row of protons just sitting there creating field lines. The field lines are as simple as that picture could, they're as simple as they can be, given what's caused them, but it's different from the picture formed by one dot, right? Every situation in the universe, every shape of charge creates a different shape of field lines. As long as the situation is stable, the field line picture should be stable. But if one picture of charge is different from another picture of charge, then the picture of the field line should be different. So if now I'm saying, what if instead of a static line of charge, or what if instead of one sitting point of charge, what if we had a flow of charge, a flow? I'm going to turn the page in a moment, obviously, but I'm asking you to think about it in your own for a minute. If we had a flow of charge, like a current, what that would be a changing field line picture. It would definitely change the field lines, right? Charge is not just here, it's going over there, it's going over there, going over there. But then a new charge is over here, going over there and going over there. Like we have a continuously updating, changing field line picture. So there's no way it's just going to look like a sunburst. And there's no way it's just going to look like spikes, because if it's flow, that's different from just a static line of charge, right? Somehow flow is going to have to create a picture that's different from those other two pictures, but it's going to have to be a picture of field lines that's as simple as it can be given a flow. And what is a straight line of flow? I'm reminding you again, I'm saying it's a change. Flow is change. It's motion of charges. But it's continuous motion of charges. In other words, I'm saying if we have charges flowing through, they must continually be changing those rays of field lines. They must be continuously changing them, but eventually those continuous changes must fall into some new pattern. If we have stable flow, we must get eventually some stable pattern of field lines that's unlike the other two patterns, because it's caused by something new, by a flow, but it must be as simple as it can be given that flow. The simplest, most symmetric picture that I can imagine that field lines would fall into if they were caused by not a point of charge and not a static line of charge, but by a flow of charge, a change, a continuous change, a continuous motion of charge. The simplest possible picture I can imagine, and the simplest picture that does exist, is more like this. Now, this is terrible. I'm going to give you a picture on the web in a second, but what I'm saying in this picture is that if we had flow of charge, well, I'm going the wrong way. Yeah, if we had flow of charge represented by my thumb, like if we had continuous current going like this, the field lines would fall into a pattern, like the protons would start changing those rays, and the rays would eventually fall into a pattern that would look like my fingers. The field lines would wrap around the flow. They would form closed paths around the long, straight flow. They would form circles at every point around that flow, circles that would go on infinitely in space, like field is supposed to go on infinitely in space, and they would get farther and farther away from each other in space as we got farther and farther away from the current, from the line of flow itself. But they would wrap around, they would be circles, they would form closed paths, loops. In other words, they would loop around the flow. And if the flow, if the flow, sorry, we're going like, am I doing it right? If the flow were going like this, they would circle around it in directions like that. Remember, field lines always have to have density and direction, and they have to go on infinitely. These would follow all the rules of field lines. And this would be, again, the simplest, most symmetric picture that I could possibly be envisioned or drawn or created around this arrow. Like, again, I'm saying around from a dot, you get bursts. From a static line, you get spikes. But from a moving line, if the rest of space has to know, not only is there a line of charge down there somewhere, but it's moving in a certain direction. See, if it knows it's moving in a certain direction, somehow that direction has to be, that motion has to be conveyed to the rest of space. It would not be good enough for there to just be spikes, because that would tell the rest of space that there's just a line of protons sitting there. But if there was a line of protons marching there continually in some velocity at some current rate, then that fact would have to be known or conveyed to the rest of space, and particularly the direction and speed of it. So the way it works is, so spikes would not tell you that. Spikes would go out if those were protons, and they'd come in if there were electrons. We would never know if the protons were moving left or right from spikes. But from loops, the rest of space would know, because if the current is flowing this way in the direction of the thumb of my right hand, the loops would loop around it like this. And if the current went like that, the loops would go like this. In other words, from points, we get rays. Around vectors, we get loops. Loops are the simplest possible, the most symmetric pattern of lines that could be caused by a vector, a continuous vector, a continuous change, a continuous flow, a straight line of flow that has not only length, but direction is much more, is just enough more complicated than a sitting point that the simplest picture it could make that would convey all of its details. The simplest, most symmetric picture that would be created by a flow with some direction would be loops around the flow. I'm going to say it one more time, then I'm going to go on, but it definitely is one of the questions. A point of charge creates rays of field lines. A flow of, and a line of charge creates spikes, same idea. But a flow creates closed loops, closed paths, loops, circular loops around it at each and every point. And now here comes two more questions. Wait, actually, I'm even going to pause there for 1 second. I just want to make absolutely sure, because that's a really big point. I'm saying now what I'm really trying to say is, as long as you get how field lines work from the whole first hour that I spent trying to drum in that they're all about symmetry and asymmetry, then do you get that if you continuously updated the field, it would fall into this? I mean, you may not, do you basically get what I'm saying? Hold on, I'm going to switch the view just to make sure I see you and you see. Hold on 1 second. Could you put an electronic thumbs up if you basically, if you found the question that says that a straight line of flow causes field lines to loop around it? Raise your hand if you found that question somewhere in the thing. Okay, that's Carly. Thank you very much. Is that just Carly? Okay, I want you all to catch up with me because it's not going to. Thank you, Ruby. Awesome. That's true. So again, I'm just asking somewhere in there. If you're with me, the takeaway I'm trying to say right now is something to the effect that long straight flows of charge make lines of field loop around it. Thank you, Antonique. Okay, that's awesome. That's 3. Anybody? Okay. And again, I'm saying that actually makes sense if you understood everything I was saying before. It's not just like a raw memorizer out of nowhere. But okay, I'll accept. So 4 of you. I hope the rest of you. Should I go on? Okay, raise your hand if you're with me right now. If you hear me at all right now. I mean, your electronic hand. Like, thank you, Jessica. Awesome. Like. Thank you. And who's that? Okay. Thank you, Anthony. Thank you, Ruby. Thank you, Manoj. Okay. Thank you. Yes. Thank you, Joseph. Okay. Awesome. Awesome. Just making sure, because it doesn't get, okay. Because, we've got like 30 more minutes. Awesome. And it's not going to get much more mathematical from here, but it does get a little faster from here. I had to lay those down so that you could, okay. Okay. Cool. Cool. All right. Now I'm going to say a couple more questions you're going to answer right now in there. When this happens, a flow of charge. Well, I'm thinking of flow of charge as a constant change of charge. If you think about it, like I'm thinking of a flow as like a river. I'm thinking of it as we're changing the electric field, but we're changing it in a constant, reliable, steady way so that we're rearranging the field lines, but they should eventually themselves fall into a new pattern. That's what a new stable static pattern. And that static pattern is these loops. That's what I'm saying so far. I'm now going to say 2 things about that. Number 1, this new shape of the field lines, these loops, this new thing that results from someone's here, sorry, is often called, is what you actually know as the magnetic field. Okay, I'm just saying that, like, what the magnetic field ultimately is a name for this effect. That if the electrostatic field is what's caused by a point of static charge or any and every and all points of static charge, when charge just exists, it creates these E field lines. Once charge starts flowing, once we have moving charges, that is, once we have changes in the electrostatic field line picture, the new picture that results, the change in the E field lines is called magnetic field lines. Again, when I'm in, like, literally, that's what magnetism is. Literally, the magnetic field is field, but it's what's caused by flow of charge rather than just the existence of charge. And I keep using the word flow to reinforce that when you picture flow, when you picture current, you're picturing motion. So you're picturing a change in the field, but you're necessarily picturing steady motion. You're picturing motion that falls into place and becomes like a river. Like whenever you stare at a certain point in a river, you do see that the river is flowing, but you always see the same thing. You see the same amount of water right in front of you, passing the same amount of time, right? It's steady flow. So similarly, all the electric field lines that were bursts will fall into a new pattern as long as we have a pattern flow of change called current. What current causes is this new pattern of field lines that loop around and are called magnetic field lines. That's definitely one of the questions. Oh, and Ruby, I'm sorry. Or are you still raising your hand from before, or you have a question? Sorry, or you might be still raising your hand from before. I'm not sure. Hold on. Let me just. You're okay. You're good. Okay, 1 second. Let me just. One second. I'm just. Okay. So first of all, one of the questions is that these loops are called magnetic field lines. It doesn't even necessarily, that's just something good to know in a way. You don't even necessarily even have to know that, although it does put some things in perspective to know it. But here's the other reason I want you to know it is that just like one of the questions was, you do need that epsilon naught number to calculate the precise electrostatic field magnitude and direction. Like if you're trying to be numerical and precise about the electrostatic field, you need that universal constant epsilon naught. Just like you need the universal constant of G to calculate the precise gravitational field. And we just need it to make all of our units stay within the metric system. Okay. It's just a proportionality constant. Similarly, one can calculate the precise numerical magnitude and direction of this thing that I'm now calling the magnetic field. I'm not saying you're going to do it on your test. I'm not saying you have to, or even that I want to, but it certainly can be done. And when it's done, what I do need you to know that is important is just like there's a universal constant for the gravitational field, and there's a universal called capital G, and there's a universal constant for the electrostatic field called epsilon naught, that E looking thing, 8.85. There's a universal constant for the magnetic field that's called mu naught. It happens to be equal to approximately 1.26 times 10 to the negative 6 henries per meter. You don't have to know the number. You just have to know that the number is called mu naught, and it is to the magnetic field as epsilon naught is to the electric field. That is definitely one of the questions. You can find it. Okay, wait, so that's definitely one of the questions. And if you want to put in the chat to help each other which question it is, or if you want to say in the chat whether the answer is true or false, because I actually can't remember how I phrase it, feel free to tell your colleagues who are paying attention. That's great. Now, but that was definitely a question. Mu naught is needed for the magnetic field numerically, just like epsilon naught is needed for the electrostatic field. Now, someone, direct chat person, happens to be a direct chat person who asked something else that was very good, but he or she just asked, does the loop happen in a wire? Okay, very good question. What I'm saying is, oh yes, okay, not in, but around, yes. I'm saying right now that every time you guys created a steady current in your lab, when you created current, you had charge flowing down a long wire. I'm now claiming, oh yes, that wire was creating loops of field lines around the wire and extending everywhere. You were creating a little magnetic field when you did that. You didn't care. It didn't affect you. You weren't asked to measure it. Like you can't see it. It's just field. But for sure, if we had put like iron filings near your wire and like controlled all the other circumstances or whatever, for sure, yes, whenever current goes through a long straight wire, it creates little loops of field lines around it called magnetic fields, and they ultimately are responsible for what's happening in iron filings and iron hunks. In fact, I'll say very quickly, what's really happening in a hunk of iron, let me back up for one quick second. Every single atom, if you really think about it, even a hydrogen atom, has one electron going around and around all the time in its orbital. That is a little current loop. That's a little circuit. Honestly, every atom is a little circuit. every atom is a little bit of current in a loop going around forever. Every atom does cause a little bit of magnetic field. Every atom is a little magnet. However, most atoms in most materials, whether it be hydrogen or wood or whatever, most molecules, all the atoms are are not aligned. All of them are arranged in such a haphazard fashion, or a fashion that obeys a certain set of rules, but not a rule that has anything to do with their electron orbital directions, that in most materials, all the electron orbitals are like this. So they're all the little magnetic fields are canceling each other out, kind of like we were talking about earlier in the class. The vector sum of all those field lines wipes itself out. So in most materials, you have all these little magnets that are all pointing in different directions and all wiping out the net effect. But in some materials, like iron, what makes iron iron, what makes it special to us, is that it just happens that that's the material where all of the electron orbitals happen to be all lined up, as though, so iron, and a hunk of iron is as though we took one wire and wrapped it in a super tight coil, a helix, all the way around a toilet paper roll or something to that effect. Like a hunk of iron, microscopically, is equivalent to a really tight coil of current carrying wire. That is, it's a bunch of little loops of wire that are all lined up with each other, so that all the little magnetic fields reinforce each other and create one big magnetic field. And then iron ends up attracting to other iron, if it's oriented one way, or repelling if you orient it the other way. So totally a great question from direct chat person. I'm saying, oh yes, any current carrying wire absolutely creates these little loops of field lines known as magnetic field lines. And the longer the wire, the more the loops. But whether we care about their effects or not depends on what else is going on. But absolutely, yes. Now, we've got 20 minutes. We are actually almost there, believe it or not. Here's where it really starts to get wild. I mean, based on exactly that direct chat question, again, who's the name of the person I will never reveal, except I totally will. Because here's the next question. Okay, so what I've said so far is like static point creates simple field line picture like this. Line of charge creates spokes like this. Flow of charge, like, in other words, constant change of field picture creates new picture of loops. Well, now, and we really are almost there, we have to do like one more abstraction. What happens if we start changing those loops? Like, what happens in the lab if you don't just have steady current going through your wire? What if you very deliberately, and with measurement tools and with isolating from all other effects and stuff, what if you start slowly changing the current in your wire? Like every second you bring the current up 1 more milliampere or something like that. What if you start increasing or decreasing the current in your wire, but at a steady rate, right? In other words, what if we go up 1 more derivative level? What if we don't have current equals a constant? What if we have current equals some kind of constant times time, right? Like 4 milliamperes of current per every second. What if we have that? Well, then those loops, right? Those loops now have flow. So now this line is not just flow, but it's changing flow, right? So the change is going to change those field lines. Like, because we now have stronger and stronger charge here, or like now the charge is getting stronger, so the lines have to change. They have to get more dense, right? And then they get even stronger, so they have to get even more dense. So the loops around this line, they're changing. They're going to get, in effect, tighter and tighter, those loops, if this current gets stronger and stronger. So they're going to create a new picture. But again, if we do this in a steady way, if we increase the current in like a linear, a directly proportional fashion, like I equals some constant times T, then eventually these changing in our loops must fall into place into a new stable picture, but it just has to be a different picture from the old one. So what will we get? Well, if you think about it, all we're really doing is we're taking our long loops and we're turning them into flows, right? So going back to Manoj, direct chat person's question, if we now put flow in these loops, if they're not just stable loops, but they're flowing, they are like long lines of flow. They're like little currents that will create loops around them. I'm saying, and this is very important, and again, I'm watching the clock. I promise I won't keep you but maybe 1 minute over, and we're almost there. But if you follow me so far, that a line of flow will create loops around it. That's a line of steady flow will create steady loops. And any segment in that loop is like a line unto itself. Just like this line, by the way, was probably part of some larger circuit that was in your lab, right? Like if you zoom in enough on any big loop, you look at a little segment. Well, this segment was creating these loops. And it did so because it had flow. If there's flow in these loops, then that's going to create loops around the loops, right? It's going to, if these loops are flowing, it's going to create a loop perpendicular, interlocking with that original loop. We'll get like, so here will be a loop, we'll get another loop like that, and here and here and here, everywhere, right? We'll get another layer of loops, I should say. If we originally had vertical loops, we're now going to get horizontal loops, for example, right? And if the current, that's if the current is increasing or decreasing in time, if we have a change in the change. Now, if that's all we have, if the current was steadily increasing, like not I is a constant, but I is a constant times t, if I is a linear function of t, if it's directly proportional to time, then we'll have a line that will create loops, and the loops will create loops, and that'll be it. We'll have like a layer of loops and a layer of loops. Complicated picture, but not that complicated. A terminable picture, that will be the picture. But can we go one more layer? Sure. What if we made a current that was quadratic, that was like I equals 1/2 AT squared, like a current that was like not just increasing, but like accelerating? Then what would happen? Well, then our flow would create a loop. The loop would create a loop. That loop would create another loop, and then it would end, right? So now we're about to get to a couple of math questions in there. And this might bring you back to like physics 203 or whatever. Like what I'm saying is we could create current that changes. Flow is already a change. Flow creates loops. A change in a flow is a flow in a loop. So a changing flow creates loops on loops. As long as our current, as long as our flow is some algebraic function of time, like a quadratic, then there's a finite number of derivatives, right? Like you can only take 2 derivatives of 1/2 AT squared, and eventually you get to a constant function, right? And after that, you're at 0, and then you're just 0 forever, right? Like you can't, eventually you take 2 derivatives of a quadratic, you eventually hit a constant function. If you take 3 derivatives of a cubic, you hit a constant function. That's definitely one of the questions. It's phrased slightly differently, but that's definitely one of the questions. However, there are some functions that you know from this class, like cosine functions or sine functions or e functions. There are functions where you can take derivatives forever, and you just keep taking derivatives forever, right? Imagine if you had a current that was like, for example, a cosinusoidal function of time, right? A current that had a velocity, but also had an acceleration, but also had a jerk, but also had a whip. Just like everything we talked about when we originally talked about that mass going back and forth on a spring, right? The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine, and back, and we keep going forever. If you made a flow like that, then what would have to happen is the flow would create a loop, right? But then there'd be flow through the loop. So the loop would create a loop. The loop would create another loop. Each loop would be perpendicular to the last loop. Each loop would be interlocked with the last loop. The loops would keep flipping in orientation from positive to negative to positive to negative, right? And this process wouldn't stop. This is definitely one of the questions. And we have 13 minutes left, but that's plenty of time for me to get to this point. Those loops would never stop as long as the flow that you originally made never stopped in derivatives. As long as the flow was a changing flow, as long as it was an infinitely flowing flow, and I don't literally mean infinite, I mean infinitely differentiable flow, then it would keep, then again, you'd have a flow, like if you had a cosinusoidal current, which is called AC, by the way, if you had current that was going back and forth, like a mass on a spring, right, then there's no end, then there's no end to the rates at which it's changing, yet it totally has a steady pattern, just like a mass on a spring, right? It has a period, a frequency, an angular frequency. Like if you looked at a current that was going back and forth cosinusoidally, it wouldn't make your head spin. You could totally get the pattern right away. In other words, it'd be infinitely differentiable, but it would be a stable, steady, cyclical picture. So what would we have? What would that form? It would form a picture of lines that was infinitely complicated in a way, infinitely asymmetric in a way, but stable and steady. What would it look like? It would look like rings forming other rings, running out of space, running away from the original current, going off into space forever. It would be rings forming interlocking rings forever in space. The rings would propagate out from the current in the manner of a wave, right? This oscillation of charge flow would create would create a vast collection of oscillating rings that would go out in space. And if you traced with your eye, you would see a pattern of patterns of these rings, much like crests and troughs moving out in space. And indeed, the field picture would be a big picture of, now it really would be a sea of information. In other words, now it would be a sea of choppy information. It would be a sea of information with crests and troughs, meaning rings like this and rings like that and rings like this and rings like that, going on and on forever, bumps and valleys that are continually reinforcing each other and continually ebbing and flowing out. And indeed, the electric field would then be a solution. This is a question in one of the questions. It would be so much a wave, not just as a physical, not just as a sort of rough visual picture, and not just as a concept, but mathematically, we would now find, if we updated the charge, if we made charge flow that continuously updated itself, that was continuously sending new updates to information out into space, those updates would travel so rigorously, like in the manner of a wave, that our old wave equation, remember our wave equation, d2y dt squared equals constant times d2y dx squared. Remember our old equation for waves said that at every single point in space and time, the second time derivative of vertical position had to be directly proportional to the second space derivative of vertical position. That's what a wave was when it was crests and troughs along a one-dimensional string. Now I'm saying that would be true for the magnitude and direction of the field. The second time derivative of the electric field would now be directly proportional to the second space derivative of the electric field at every single point in space and time. The electric field would now be a solution to the wave equation. That's definitely one of the questions. I don't remember if it's true or false, but that's definitely one of the questions. Again, what I'm saying is if we send changes to the electric field in a way that is continuously changing itself, if we create a current that is like a, for example, cosinusoidal function of time, then the continuous updates to the electric field, the continuous flowing changes the continuous new information about what charge is doing here, like every minute, every moment, charge will be doing something different over here. The rest of space has to get every moment the new update of what the charge is doing. Every moment it'd be traveling in a different direction, at a different speed. Every moment space would have to get this update. Those updates would travel out in interlocking field rings that propagate according to the wave equation. And we are literally almost done. We are literally almost done. Already, I think this is very interesting, but two things. One, the wave equation, remember, is second partial time derivative of variable is directly proportional to second space derivative of variable, right? That's our original wave equation. The constant of proportionality, you might remember, is the square of wave speed. Now, that's definitely one of the questions. One of the questions says something like the constant of proportionality in the wave equation is proportional to wave acceleration. It says something like that. It says something like wave acceleration. I'm telling you right now, find that question. That is false. The true thing is that the constant of proportion, and maybe that's a word I'll change for the actual final exam to make sure we're still all paying attention right now. But I'm saying that I want you to remember that in the wave equation, second time derivative is directly proportional to second space derivative. The constant of proportionality is the square of the propagation speed. Well, that's always true of any wave at all. In this wave that I'm talking about here, that we're ending the course on, when the electric field, when changes in the electric field propagate out in these rings that are traveling through space forever, the wave equation is d dt squared equals 1 over mu naught epsilon naught times d2e dx squared. In other words, this is one of the questions. The constant of proportionality in this wave equation is, not surprisingly at all, 1 over the constant of proportionality for the electric field, epsilon naught, times the universal constant for the magnetic field, mu naught. Like, I'm not saying you would have known that, but when you hear it, it's not a surprise. The constant of proportionality for the rate at which electric field information propagates, the constant of proportionality in that wave equation, I'm just telling you, is 1 over mu naught times epsilon naught. But here's the kicker, and I know we have 6 minutes left. And maybe I'll say that one more time just to make sure. I'm saying that when updates to the electric field are set, when the charges causing the electric field are set up into a flow that is continuously changing in a patterned but infinitely differentiable way, like when the current is going back and forth like an oscillator, so that at every single moment where the current is different, how fast it's going is different, how fast it's accelerating is different, and yet it's still some sort of pattern, right? When you do that, when you make a infinitely differentiable pattern of continuous change to charge flow, you create you send out updates through the electric field. That what happens to the picture of the field lines is ripples, these interlocking rings ripple out through the field lines. They ripple out through this sea of information, and they obey the wave equation. And the constant of proportionality in that wave equation is 1 over mu naught times epsilon naught. Not surprising, because those are the two constants that govern the two types of fields that are interlocking themselves and traveling out. The thing that is surprising is that if you do the math, if you on a calculator, not right now, or you can if you want, or later check, if you actually take the square root of 1 over the mu naught number times the epsilon naught number, right? If you take the square root of that, remembering that the constant of proportionality for the wave equation is the square of the wave speed, of the wave propagation speed, I'm telling you the constant of proportionality here is 1 over mu naught times epsilon naught. That's one of the questions. That means that's the square of the speed at which this thing propagates. If you take the square root of this random number, epsilon naught, times mu naught, and you put it under 1, what you get is 2.99 times 10 to the 8th meters per second, i.e. the speed of light. What I'm saying is that if when updates to the electric field ripple out through the sea of information that is the electric field, those ripples travel at the speed of light i.e., that is what light actually is. What light is, I know I have 3 minutes, and then we're done. What light is, what the motion of light is the motion of ripples through the electromagnetic field. What light is updates in the electromagnetic field. What light is how one point in space tells another point in space, we've got a new situation here. Our charge just moved over, or more charge just got added to us, or there's a flow of charge or whatever. When there's a flow, when there's a change over here in space, that information, that change in the information that already was everywhere in space, that change ripples out through the field lines in these rings, and we experience it as light. Light is updates to the electromagnetic field, and we know that because this whole process happens at the speed of light, which no one knew until they knew. And what that means to bring the course full circle is, remember, originally we now look back at the beginning of the test if you want. Remember, we spent all this time analyzing sound waves, and we're telling ourselves over and over and over again that we believe that sound is real, even though it's not material, it's not physical, it's not particular, it's not thingy. We believe that when sound goes from my mouth to your ears, that something real goes from my mouth to your ears. Well, what really goes is information, numbers. Like when I sing the note A, a vibration of a rate of 400 cycles per second somehow goes from my mouth to your ears. How? Because a bunch of air molecules in between my mouth and your ears all vibrate back and forth in such a complicated but intricate, beautiful pattern that a raw piece of information goes from my mouth to your ears. We believe that the information can travel because we believe in a sea of material that is all oscillating together to allow for that ripple. Now, the last thing in the course I'm saying is that's cool enough as it is, that we believe in the existence of raw information. But now we're saying that raw information sits everywhere in the world in the form of a field. Abstract, immaterial information sits everywhere in the world in the form of a field. And every time we send light from one place to another, we're sending raw ripples through that raw information. That light is a double abstraction. It is a ripple, which is not material, in a sea of stuff, which is not material. Light is updates in raw information, that it's ripples, pulses, propagations in the electromagnetic field. That's the point of the course. That's the point of this test. I'm done. You've been awesome. I'm going to hang out for a second. If there's any last minute questions or any concerns or anything, I'll stay here. But I'm done. Yes, have a great summer. You do your job. I'll do mine. You'll get good grades. I will miss you deeply. Yes, have a great summer. I'm done. And you'll get stuff back, blah, 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 blah. But just do this thing. It'll be posted tomorrow. But I'll hang out for a second if there's any questions. But thank you guys very much for being so patient. Yes, have an amazing, yes, you too. In particular, yep, you too. Thank you guys. And I'm stopping the recording. But thank you very much. Thank you. Have a great summer. For reals. I hope to see you physically, some visit. Yes, have a great, okay. Yes, thank you guys. Thank you.